Congratulations, my dear students! You have come to the last part of our course, the inverse trigonometric functions and trigonometric equations. To start our discussion, let us recall the concepts on functions. A function is a correspondence or a mapping between two sets x and y in which the element of set x corresponds to exactly one element of y. In the given illustration, we have set x having elements negative 1, 0, 2, 3, 10. And we have set y having elements negative 2, 1, 8, 10, and 12. Now, negative 1 is mapped to negative 2, 0 is mapped to 8, 2 is also mapped to 8, 3 is mapped to 10, and 10 mapped to 12. As you can see, the elements in set X is mapped to exactly one element in set Y. A correspondence can also be illustrated using a graph. Now, to know whether a correspondence is a function or not, we can use the vertical line test. That is, by drawing a vertical line over the graph. Now, what if we draw a vertical line over this portion? Now, if the intersection of the graph and the vertical line is only one or at exactly one point, then we can conclude that the given correspondence is a function. The inverse of a function exists if no horizontal line intersects the graph of a function more than once. This means that a function is a one-to-one correspondence. And if the point AB is on the graph of f, then the point BA is on the graph of the inverse function, denoted by f raised to negative 1. The graphs of the function and its inverse are a reflection of each other across the line y equals x. Now let's see whether the inverse of the function sine x exists using the horizontal line test. Let's draw a horizontal line over the graph and count the number of points of intersection. Now using this, we can already see 2 points of intersection, and if we extend the line to the right or to the left, we can see a lot or infinitely many points of intersection. Now let's explore the graph of the cosine function. Using the horizontal line test, let's determine whether the inverse of cosine x exists. Now, if we draw a line anywhere on the graph, we can also see that there are infinitely many points of intersection. Therefore, the inverse of the function cosine x does not exist. Now, what about if we have the function tangent x? Does the inverse of this function exist? Now, if we draw a horizontal line over the graph of tangent x, we can also see that there are infinitely many points of intersection. Therefore, the inverse of the function tangent x also does not exist. Now, take a look at the graph of the function secant x. Can you tell whether the inverse of this function exists? Let's draw a horizontal line over the graph. Now, constructing a horizontal line over its graph, we can see that there are also many points of intersection. Therefore, the inverse of the function secant x does not exist. What about the cosecant x? We can draw a horizontal line and we can also conclude that its inverse does not exist. Now looking at the graph of the function cotangent x, we can also conclude that its inverse does not exist. By drawing a horizontal line, we can see that there are many points of intersection. Based on the horizontal line test, the inverse of trigonometric functions does not exist unless we will only consider only a portion of the graphs. Now let's consider only this portion from negative pi over 2 to positive pi over 2. Now as you can see, we can already draw a horizontal line over the graph, and we will see that the point of intersection is only 1. Therefore, at this interval, negative pi over 2 to positive pi over 2, the inverse of the function exists. Graphing the inverse of the function sine x, we would be able to have this curve. We can say that the domain of the inverse function of sine x is the closed interval negative 1 to positive 1, and the range is the closed interval negative pi over 2 to positive pi over 2. Now what about the inverse function of cosine x? If we will consider only this portion from 0, okay, closed interval 0 to pi, we would be able to draw a horizontal line and see that the intersection is at exactly 1 point. Graphing the inverse of cosine x, we would be able to have this curve. We can say that the domain of the function is the closed interval negative 1, positive 1, and the range is the closed interval 0 to pi. Notice also that the domain and the range of the original function has been interchanged. Now what about the inverse function of tangent x? Considering the closed interval from negative pi over 2 to positive pi over 2, we can already see that if we draw a horizontal line over the graph at this interval, there will always be 1 point of intersection. Therefore, we can say that its inverse does exist. Graphing the inverse of tangent x, we would be able to have this curve having a domain at negative infinity to positive infinity. Or we can also have the set of all x's such that x is an element of the set of real numbers, while its range is open interval negative pi over 2 to positive pi over 2. Now for the inverse function of cosecant x, we will consider the interval, the closed interval, negative pi over 2 to positive pi over 2. Now, considering only this portion of the graph, we can clearly see that the point of intersection of the horizontal line and the graph is exactly at 1 point. Graphing the inverse of the function cosecant x, you would be able to have this curve. Now, looking at the graph, the domain of the inverse of cosecant x is the union of the half-open interval to the left, negative infinity to negative 1, union, half-open to the right, from positive 1 to positive infinity. Now for the range, notice that 0 can never be a value for y. Therefore, you will have the interval, half open interval to the right from negative pi over 2 to 0, union 0 to positive pi over 2. Now let's have the inverse function of secant x. We consider the interval from 0 to pi. Now as you can see, we can draw a horizontal line at any point, and we can see that there is only one point of intersection. Therefore, the inverse of the function secant x at this interval exists. Now graphing the inverse of the function secant x, we notice that -1 is part of the domain and +1 is also part of the domain. So we can say that the domain is the half open interval to the left, negative infinity to -1, union of the interval that is half open to the right from +1 to positive infinity. Let's determine the range of the inverse function of secant x. Notice that pi over 2 can never be a value for y, so therefore we will have the interval, which is half open to the right, 0 to pi over 2, union pi over 2 to pi. Notice that pi is part of the range. Now let us explore the inverse of cotangent x. Consider the interval from 0 to pi. Okay, we can draw a horizontal line at any point. We can always have one point of intersection. So therefore, if we will restrict only the function at 0 to pi, the inverse of cotangent x just exists. Now graphing its inverse, we would be able to have the curve. In this graph, we can see that the domain is the set of real numbers, or the interval from negative infinity to positive infinity. The range is the open interval from 0 to pi. Now here is the summary of the inverse function of sine, cosine, tangent, cosecant, secant, and cotangent. Take a look at the domain and the range. Be careful of the signs and symbols, as it is important in our lesson as we solve trigonometric equations. Trigonometric equations are equations involving the trigonometric functions. We solve trigonometric equations just as we solve algebraic equations. However, this time we shall include the properties of trigonometric functions, including the trigonometric identities. Before we start solving trigonometric equations, I want you to get acquainted with the inverse properties of the sine, cosine, and the tangent function. For the sine of the inverse sine x, we will have x for every x in the closed interval -1, 1. For the inverse sine of sine x, it's equal to x for every x in the interval in the closed interval negative pi over 2 pi over 2. For cosine of the inverse cosine of x, it's equal to x for every x in the closed interval negative 1, 1. For the inverse cosine of cosine x, it can be simplified as x for every x in the interval 0 to pi. For the tangent of the inverse tangent of x, that's equal to x for every real number x. Then for the inverse tangent of tangent x, it can be simplified as x for every x in the closed interval negative pi over 2 pi over 2. Now in case where x is not in the interval, now in case x is not within the given interval, then these properties cannot be applied. Now let's work on example number 1. Find the exact value of arc sine of square root of 3 over 2. This means that we have to get the measure of an angle having a sine ratio that is equivalent to square root of 3 over 2. If we will draw, or if we will illustrate this using a right triangle, we will have y, let y be that measure of an angle. And since we have the sine function that is equal to the ratio of the opposite side over the hypotenuse. So this means that the opposite side is square root of 3 and the hypotenuse is square root of 2. So forming the equation, you will have, okay, let y be that angle. So y will be equal to sine, arc sine of square root of 3 over 2. Now, if we will have to get the sine ratio on both sides, we will have sine y is equal to sine of the inverse of square root of 3 over 2. Applying the property of the inverse for sine, we will have sine y equals square root of 3 over 2. Okay, it means that the sine of the inverse, it's just equal to 1. So therefore, we will have the equation sine y equals square root of 3 over 2. Remember that the domain of the sine function is from negative pi over 2 to positive pi over 2. So we have to get that angle whose measure, we have to get that angle between negative pi over 2 until pi over 2. In order to solve this, we can use our hand trick, the table of values which we have studied in the previous SLM, the special angles. Remember that the angle having a sine ratio that is equivalent to square root of 3 over 2 is 60 degrees or pi over 3 based on our table of values. Therefore, the inverse of sine square root of 3 over 2 is pi over 3. Now let's have example number 2. Find the exact value of arc cos of negative 1. So just like what we did in the first example, we let y be that angle that is equal to negative 1. Okay, we get the cosine function on both sides, so we will have cos of the inverse of the cosine of the inverse of -1, then on the right side, we will have only -1. Now using your calculator, you can press shift cosine -1. That will give you 3.1416 or pi if your calculator is in radian mode, but if it is in degree mode, you will get 180. So therefore, y is 180 degrees or pi, since the domain is the closed interval 0 to pi. Now let's solve the exact value of arcsecant of 2. Note that arcsecant of x is equal to the arc cosine of 1 over x. So if you have arcsecant of 2, that is equivalent to arc cosine of 1 over 2. Now we let y be equal to that angle, having a cosine ratio of 1/2. Getting the cosine ratio on both sides, we will have cosine y equal to the cosine of the inverse function of cosine 1/2. So we will have cosine y equal to 1/2. Now take a look at our equation using our calculator. We can have shift cosine open parenthesis 1 divided by 2. That will give us 60 degrees. So therefore, y is 60 degrees, or in radian measure, that is pi over 3. So remember that the domain of cosine is the closed interval 0 to pi, and pi over 3 is within the given interval. Hence, arcsecant of 2 60 degrees, or pi over 3. In the previous example, we are dealing with special angles and quadrantal angles. This time, what if we are not having 60 degrees, 0 degrees, 30 degrees, and so on? Let's have example number 4. Evaluate the arctan of 3 and approximate the answer in 4 decimal places. Just like what we did in the previous example, we let y be equal to arctan of 3. Remember that the domain of the tangent function is the open interval -pi over 2 until +pi over 2. We have to get that measure of the angle having a tangent ratio that is equal to 3. Now we have to get the tangent ratio on both sides, so we have tangent of the inverse tangent of 3. Then we simplify, tangent y is equal to 3. Now using your calculator, we will have, we press shift tangent 3. We have 1.2490405. So since this is not exact, we change the symbol to approximate symbol. So we will have 1.2490. since we are asked to approximate the answer in 4 decimal places. Make sure that your calculator is in radian mode to get 1.2490, or you can have it in degree mode, but make sure to convert that to check whether it's within the interval negative pi over 2 until pi over 2. Now let's work on example number 5. Evaluate arcsine to approximate your answer in 4 decimal places. So we do the same in solving this problem. We let y be equal to arcsine of 2. Now take note that y should be within the range. Now we get the sine ratio on both sides, so we will have sine of the inverse sine of 2. Then we will have sine y equal to 2. If you will use your calculator, then you will have shift, then sine 2, then it will give you math error. Why? Remember that the value should be in the interval -1, +1. Take note that the domain of the inverse function is -1 to +1. Now 2 is not within the interval, therefore there is no angle which satisfies the given condition. Let's have example number 6. Without using a calculator, find the exact value of cosine of the inverse cosine of 1/3. Now, to start our solution, we have to determine whether 1/3 is within the interval -1 to +1. We can use a number line to visualize whether 1/3 is within the range. So if we have -1, we have 0, then we have +1. Then 1/3 is here. So therefore we can apply the inverse property, which is cosine of the inverse cosine 1/3, which is just equal to 1/3. Now let's work on example number 7. Without using a calculator, find the exact value of inverse sine of sine 7 pi over 3. Now let's determine whether it's within the given interval. Okay. The sine function has the domain -pi over 2 until pi over 2. Now 7 pi over 3 in mixed number form is equal to 2 pi over 3. Now 2 pi over 3 is beyond the interval -pi over 2 pi over 2. Therefore, we cannot directly apply the inverse property. In this case, we shall use reference angles. Let's determine the quadrant at which the terminal side of the angle lie. Now, the angle is in standard position. Now, 2 and pi over 3, 1 full rotation, then 1/3. So, therefore, the terminal side of the angle lies on the first quadrant. So, this is pi over 3. Now, sine pi over 3, using our handshake, okay, pi over 3, this is pi over 3, square root of the number of fingers below, over 2. So, sine pi over 3 is equal to the square root of the number of fingers over 2. Okay. So replacing 7 pi over 3 with the exact value, okay, so let's write first the original expression. So we have sine, inverse sine of sine 7 pi over 3. That will be equal to inverse sine of square root of 3 over 2. Now we let y be equal to inverse sine of square root of 3 over 2. Then we get the sine function on both sides. So we have sine of the inverse sine square root of 3 over 2. Simplifying, we will have sine y equals to square root of 3 over 2. Okay. Therefore, y is equal to pi over 3. Therefore, the inverse sine of sine 7 pi over 3 is equal to pi over 3. So let's apply what we have learned today by solving a real-life problem. One of the safety regulations require the base of a ladder 1 foot from the wall for every 4 feet of a ladder length. Find the angle that a ladder of any length forms with the ground. Now, using the information in the problem, we illustrate the angle formed by the ladder, and the horizontal distance from the foot is theta. Then we have the horizontal distance A and the length of the ladder for A. In the triangle, we have the adjacent side and hypotenuse. The trigonometric function that involves the adjacent side and the hypotenuse is cosine. So we shall use cosine theta equal to adjacent, which is A, over the hypotenuse for A. Simplifying, we can cancel A and A. So here we have 1. Therefore, cosine theta is equal to 1/4. Now, to know that angle, we have to get the inverse. Okay, we have to get the inverse cosine of 1/4. Okay, using our calculator, we can have shift, then we have cosine inverse 1 divided by 4. Make sure to enclose 1 divided by 4. So we will have 75.52 degrees. Okay, so we have 75 degrees, 31 minutes, and 20.96 seconds. So therefore, the angle that a ladder of any length forms with the ground is 75 degrees, 31 minutes, and 20.96. There are trigonometric equations which are quite complicated. Here are some techniques which you can apply in solving that kind of trigonometric equations. First, determine whether the equation is linear or quadratic in form so that you can decide the solution method. If the equation is linear in a single trigonometric function, isolate the function on one side of the equation, then solve the equation for that function. Solve for the angle by determining the function values of the quadrantal or special angle by applying the trigonometric tables. You may also use calculator. Make sure to set it on the appropriate mode. Third, if more than one trigonometric function is present, apply the fundamental identities to represent the equation in terms of one trigonometric function. If the equation is quadratic in a single trigonometric function, rearrange the equation so that one side equals 0. If the equation is not factorable, use quadratic formula. Check if the solutions are in desired interval. Use the measure of the reference angle to find the degree measures of each solutions in the interval. X is greater than or equal to 0 degrees, but less than or equal to 360 degrees, or the radian measures of each solution in the interval from x is greater than or equal to 0, but less than or equal to 2 pi. To find the general solution of a trigonometric equation in degrees, add 360n, where n is an integer, to the solution in degrees. To find the general solution of a trigonometric equation in radians, add 2n pi, where n is an integer, to the solution in radians. Now let's apply the given techniques in solving trigonometric equations. So find all the solutions of cosine x minus 1/2. Now since the equation is linear in nature, we isolate cosine x. So we will have cosine x is equal to 1/2. Applying the inverse property, so we will have inverse of cosine x is equal to the inverse of cosine 1/2. Applying the inverse property, we will have x, then inverse of cosine 1/2, we will have x is equal to pi over 3. Now, illustrating the angle, we have pi over 3, an angle in standard position. Okay, has a terminal side which lies on the first quadrant. Okay. Now, one full rotation, okay, we will have x of 1 is equal to pi over 3 plus 2 pi n. Now we can also have an angle having a negative rotation, which is negative pi over 3. Take note that cosine of negative pi over 3 is also positive 1/2. So therefore, we have to get another angle. So we have 2 pi minus pi over 3, okay, plus 2 pi n. Simplifying that, we will have 5/3 pi plus 2 pi n, where n is the set of integers. In example number 10, 2 times tangent squared x plus secant squared x equals 2 is quadratic in nature. So all we have to do is to determine whether it's factorable, or we can apply trigonometric identities in order to express the terms in a uniform trigonometric function. So let's see. Remember that secant squared x can be equal to tangent squared x plus 1. So we use Pythagorean identity. So 2 tangent squared x plus, we replace secant squared x by tangent squared x plus 1. Now we combine similar terms, so we will have 3 tangent squared x plus 1 equals 2. We transpose 1 to the other side, so we will have 2 minus 1. Now 3 tangent squared x is equal to 1. We divide both sides by 3, so we will have tangent squared x is equal to 1/3. We extract the square roots in both sides, so we will have tangent x is equal to square root of 1 over square root of 3, or simply 1 over square root of 3. We rationalize, so we have square root of 3 over 3. Okay, we have tangent x, square root of 1 times square root of 3, that is square root of 3. Then we have in the denominator, we will have 3. Now we get the inverse on both sides. Okay. Then we have square root of 3 over 3. Applying the inverse property, this will be equal to x. Then we have the inverse of tangent square root of 3 over 3. Using your calculator or your hand trick, you can see that x is equal to pi over 6. Now let's illustrate to find or to determine at which quadrant the terminal side of the angle lie. So let's draw an angle in standard position, pi over 6, that is on the first quadrant. Now, tangent pi over 6 is positive. We can also get a positive value for the tangent ratio using reference angle. Remember that on the fourth quadrant, we can have an angle Remember that we can have a positive value for tangent on the third quadrant. So if this is pi over 6, this will be, okay, take note that we have one straight angle. So determining that angle on the third quadrant, we'll just add pi over 6 plus pi, okay, pi over 6 plus pi, that's equal to 6 pi over 6. Therefore, we will have 7 pi over 6. Now, since we are asked to get only the angles within this range, therefore x is equal to pi over 6 or 7 pi over 6. The given equation in example number 11 is quadratic in nature. So we can see, or we can check whether it's factorable, or we can apply the Pythagorean theorem. Now, since we have 2 sine squared x, since we have 2 sine squared theta minus 3 sine theta plus 1 equals 0 has only one trigonometric function, we will apply factoring. So we can factor this as 2 sine theta minus 1 times sine theta minus 1 equals 0. Now, equating each factor to 0, we will have 2 sine theta negative 1 equals 0, and sine theta minus 1 equals 0. Now, for 2 sine theta minus 1 equals 0, we can transpose negative 1 to the other side. So we will have 2 sine theta equals 1. We divide both sides by 2. So we have sine theta equals 1/2. Now, we have to get the inverse, okay, of this. we will have sine of 1/2. So applying the inverse property, we have theta. Then we have sine inverse of sine 1/2. We think of that angle having a sine ratio of 1/2. Okay, using our hand trick, we have sine 1/2, that is pi over 6. So pi over 6. Okay, now pi over 6 is on the first quadrant. Take note that on the second quadrant, okay, we can also have a positive value for sine. So that is using the reference angle pi over 6 on the second quadrant. So okay, we can also have a positive value for sine. So that is using the reference angle pi over 6 on the second quadrant. So another solution would be, we will have pi minus pi over 6. So that is pi over 6. Now for sine theta minus 1 equals 0, we transpose -1 to the other side, so we will have sine theta equals 1. Now we apply the inverse property in order to get theta, and we'll have the inverse sine of sine theta is equal to the inverse sine of 1. So we shall have theta here, then we have inverse sine theta, or sine. So we have theta is equal to the inverse of sine 1. Therefore, using our hand trick, in order to get 1, we will have pi over 2. Therefore, the solutions are pi over 6, 5 pi over 6, and pi over 2. I hope you were able to get the process. Now let's solve this problem. A vegetable garden is being planted in between two buildings measuring 20 meters and 45 meters tall, which are 3 meters apart. Express data in terms of x. This angle will determine the amount of sunlight received by the vegetable garden. Now let's form two rectangles. Now take note that in a rectangle, opposite sides are congruent, and that the diagonals of the rectangles divide the rectangle into two congruent triangles. Let's say this side is x, then we will have 3 minus x here. So here we can have 3 minus x. We have here x. Okay. Now we can have here 20, then we have 45. Now expressing theta, we can have arctangent 3 minus x over 20 plus inverse tangent of x over 45. Thank you for journeying with me this semester. I hope you were able to get a lot from our lessons, and I hope I was also able to prepare you for our next course, which is Basic Calculus. See you again!